The question of how an atom can be represented and what an atom will look like if we can increase it to the size of an apple is probably one of the most popular of those questions that I was asked in the comments. Well, it's time to deal with this thing. Yuri is in touch as always, Trifonov, and today we will try to imagine exactly what an atom will be like if we increase it to the size of an apple. So, what do we know about the atom? Well, first of all, we know that it is a particle and that the atom also consists of some subatomic particles. The structure of an atom is usually described by the standard classical model, which consists in the planetary model of the Rutherford atom. However, modern ideas about the structure of the atom have changed a lot, and the Rutherford atom model has remained, except in school textbooks, as some kind of beginning of the creative path of any person studying physics. A much more objective model today is the Schrodinger model. About it was a separate piece, and there will be a link somewhere in the description of the video. Let's remember what the essence of this model is. In general, the Schrodinger model is not much. It differs from the Rutherford atom model. There's a core there too. But unlike the planetary model, where we have electrons orbiting like planets around the nucleus of an atom, here we have the probability cloud, where the appearance of an electron is most expected. There are very deep, interesting points here, which, by the way, leave an imprint on the issue that we are trying to sort out now. In fact, the structure of an atom, which is a planetary model, implies that an electron is some kind of constant standard particle that can be touched and which is quite a physical body. But the Schrodinger atom model, which is more modern, says that there is a region of probability where an electron may or may not exist. With some degree of approximation, it may happen that an electron exists both here and there at once, being a phantom. These are, as they say, the features of quantum physics and the already traditional classical wave function. All of this is a defining moment that allows us to represent the atom in a very specific way. What do if you and I were to increase the classic Rutherford atom to the size of an apple? Then we would have received a classic model of the atom, which could have been bought in all stores earlier. If you remember, there was such a model of a perpetual motion machine, where we have a central point and some orbits or something similar revolve around it. This is what an atom would look like according to the Rutherford model if we increased it to the macro level. But this is an outdated view. And if we increase it the model of the atom that we have now and is considered the most correct, then we will get that. And we will get it as unclear what. Let's note a few characteristic points. Firstly, because we have electrons, which are, so to speak, whether they exist or not, they are located somewhere all around, and an incomprehensible point will be some kind of flickering zone where different particles will periodically materialize, in particular, electrons. And these particles will create an incomprehensible, confusing cloud of probabilities. It will be like something like electronic noise. If you remember the old screens, there was even such a screensaver, where various dots flew out and digital noise was obtained. Active digital noise. This is about the same zone that will be around the nucleus of an atom. Somewhere inside this zone there will be the core itself, which you and I will not see. Even if we increase the atom, it won't change anything. With all this, it is unclear how to visualize it at all. In fact, we will be dealing with some kind of cloud that has neither size nor shape. And at the same time, everything is in some probabilistic characteristics. The size will be the same probabilistic and it will be able to change in a certain range. The appearance of the atom will be vague and look like some kind of digital noise. Well, we won't see the inside of the atom at all. Moreover, there is a high probability that light will not be able to fully interact with those particles that we are considering. The increase of an atom to some sizes is not necessary for us, it won't lead. The next important point, if each particle is located at a certain distance from each other, then regardless of whether the particle changes its position, there is some distance between the particles. This distance is determined by a number of parameters. It doesn't matter which ones are important now. Electrons and the outer particles that surround the atom, they will be located at a distance from each other, and in fact it will be like a bubbling foam, where particles appear and disappear. We have talked about electrons many times and they behave in such a strange way. And it is unclear where. The result is something like a ball, the size of an atom. It is unclear how and what to touch here. And here's the question about touching. Another popular question that is often asked in the comments under the videos about atoms. What will the atom feel like if it is large? For some reason, many people are interested in how we can touch matter if, in fact, it consists of an empty space. Here I will give a characteristic description that I have repeatedly given in my articles. Yes, any matter in fact consists mainly of an empty space, on the one hand. On the other hand, there is nothing specific about it. The easiest way to imagine this is to take two magnets and try to combine them with the same advantages with each other. Obviously, they will start to push it off. It will feel quite material to itself, and when these magnets are repelled, we can quite say that this feeling is very material. Why, then? Do you have a question about how we touch matter? Let there be 80% empty space and subatomic particles. All this is built into some structures. Whether there is a probability of location or something else, it is important that they interact with each other and repel each other. As a result of the particles repelling each other, you and I feel the same as when magnets interact. Moreover, our body also consists of particles. We also have electrons in our body, both inside and on the surface. Regardless of what these electrons are, we, having their body composition, are essentially trying to touch another body of electrons. And it is obvious that we feel this repulsion. And that's where that great headline works. You and I can never touch anything because in fact we feel the constant repulsion of particles. Now let's transfer everything to the structure of the atom and how we imagined it. We said that in order to somehow imagine an enlarged atom, we need to imagine some kind of cloud of some constantly changing digital noise. We most likely will not see the position of the core of this cloud, and some kind of abstract beam will be visible. It is not clear from what. But now we're taking it and trying to feel him. What will we feel? Well, it will be some kind of incomprehensible substance that also repels objects consisting of particles of the same name, and in fact we will touch this jelly. In fact, it's about the same as you and I touch. Let it be a ball, but for all that, yes, the atom should be quite large and we should be able to feel it. But we have already indicated that, yes, the atom is enlarged. Therefore, we can interact with him, we can easily touch both the atom and the ball, but you need to understand that since the atom does not have a definite shape and the location of the particles is enclosed in this cloud of probability, no matter how strange it may sound probabilistic, you and I cannot fully feel it. We are trying to take this ball, but the electrons ended up at another point. We touch it, and he is constantly changing shape. Therefore, even if you and I increase the atom, we still won't be able to touch it properly. It may happen that this thing will constantly change its shape. This thing will constantly change its characteristic dimensions, falling into the designated range of these sizes. With all this, it won't even look like some kind of water balloon or something so flexible. Here are the analogies that we always try to present to simplify and improve the perception of the material, are not entirely unambiguous and are not always objective. The thing is that at the quantum level to which we are moving, these analogies largely stop working. Classical mechanics is something objectively obvious and understandable. Let's say, the hammer is on the table. It represents a classic material thing or a classic material object. This classic material object can be touched. It has a shape, dimensions, and strength, and so on. When we talk about quantum particles, then everything is much more complicated and much more interesting. The thing is that quantum particles will not obey the analogies that we are trying to transfer to them. Different models can be used, but models need to be used carefully and carefully. It's the same here. When we try to imagine that we have enlarged an atom to the size of an apple and try to touch it, we do not understand, do not attach importance what is actually an atom, which is surrounded by subatomic particles of the quantum level, will behave completely differently. It will not resemble the most ordinary ball in any way. Therefore, based on some indirect factors, you can simply make such a guess that, in general, it will resemble a balloon filled with water, which will constantly deform. But at the same time, you can't touch it either. After all, it is surrounded by electrons. Our body is also surrounded by electrons. Let's just say that any matter has a similar design. Any matter in physics has a similar design, and these matters, one way or another, will interact. In many ways, by the way, based on the Pauli principle. By the way, surely you know why this repulsion happens and why we can't, roughly speaking, bring atoms together. In fact, this is a big topic that should be considered in a separate video. But I'll say it briefly, that in fact the principle of Pauli's prohibition works. Two particles cannot be at the same point, so two electrons try to push off each other. But here you can find fault with this formulation. But, anyway, I think it's useful to understand this, to know and realize that the principle of Pauli's prohibition is not only about these cells where we draw arrows up and down. After all, many of you probably remember the principle of prohibition in this form, because in the school course, we just draw cells and place electrons there, saying that they must necessarily be multidirectional, otherwise, nothing will work out, and it's never clear what the hell it's for. Let's summarize briefly. If you enlarge an atom, it is quite difficult to describe it, because it will be some kind of phantom object resembling something like a haze consisting of digital noise, constantly moving and changing in size, but not going beyond some characteristic dimensions that we can calculate. It will not work to touch this thing in the way we want to do it, because at best the analogy that fits here is a balloon that easily squeezes and unclenches. And one more thing, an atom can include electrons that are literally almost in another universe and almost in another dimension. This is a pretty big topic, and I had an article on this topic. Links are provided. There is a very interesting moment there. With a certain degree of probability, it may turn out that the electron, related to an atom, it is actually located millions of kilometers from this atom, and this follows from the probabilistic model of the location of the electron. Well, and that's probably it. Thank you all for your attention. Be sure to subscribe to the Telegram channel of the project in order to always keep in touch with each other. Some interesting updates are regularly released there. Well, see you soon. Thank you all. Bye, everyone. All the best.